In this video, we introduce the concept of the equilibrium constant. In a prior video, we have defined elementary concepts in chemical equilibrium. We have said that for a generic reaction A to give B, which needs to be reversible, we can plot the concentrations as a function of time, and it might happen, if the reaction is reversible to a significant extent, that the concentration of A follows this trend, and the concentration of B follows that trend. And then we can see that there's a point during the reaction where the concentrations no longer change on time, and then we call this a chemical equilibrium. So after this point in the reaction, chemical equilibrium is reached, and then you cannot make any further progress of reagents into products. Now what we do in this video is characterize a little bit at a quantitative level how this equilibrium works. Right? So what people found by doing measurements, so this is all a phenomenological explanation, was that the concentration at equilibrium of reagents and products, and reagents, they always followed a very interesting relationship. And that relationship was that at equilibrium, the concentration of products, B, over the concentration of reagents, A, was constant. This constant is called capital K. It's called the equilibrium constant. Now it's important that you write this as a capital case K to distinguish it from rate constants, which usually are written using lowercase k. Okay, so there's a clear distinction between the equilibrium constant and a rate constant. The equilibrium constant characterizes chemical equilibrium and is characterized by a capital letter K. Okay? So at equilibrium, what they found out is that the concentration of products divided over the concentration of reagents was the same. And this seemed to be irrespective of the type of chemical reaction that you were looking at. So for example, for a more generic reaction in which you have two reagents, A and B, to generate two products, C and D, okay, this equilibrium constant happened to be the concentration of products, the product of the concentration of products over the product of the concentration of reagents. Now something important that you're recognizing here is that these lowercase a, b, c, and d, those are simply the stoichiometric coefficients that emerge when you balance the reaction. So they can be, usually they are whole numbers that tend to be small. Okay? So it can be 1, 1, 2, 1, or whatever they are, it doesn't matter. They are just the stoichiometric coefficients, and they enter the equilibrium constant as powers to the concentration of each specific compound in the chemical reaction. Okay? So notice how this chemical reaction is a generalization of this chemical reaction that has only one reagent, one product, with stoichiometric coefficients of 1 and 1. Okay, for this chemical reaction, it turns out that, well, you have a power here of 1, a power there of 1, so you don't write them. Okay, but in any chemical reaction, the equilibrium constant can be written simply as the product of the products in the numerator elevated to the powers of the stoichiometric coefficients divided by the product of the concentration of reagents elevated to the power of the stoichiometric coefficients. Okay, something that is quite important is that this value of the equilibrium constant does not depend on the initial concentrations of reagents, right? So it doesn't matter if you start the reaction with A and no B, or with B and no A, or with any intermediate concentrations. It turns out that that value of K is immutable at a particular temperature. To illustrate this point, I'm going to write here an actual equilibrium, a chemical reaction that takes place inside our bodies, which is the isomerization of the sugar glucose 6-phosphate into fructose 6-phosphate. I'm not going to write the chemical formulas for the compounds because they are quite complicated. We're simply going to be using acronyms. That is going to be G6P into F6P. And again, these are sugars that you will study in biochemistry. This is one of the steps in glycolysis, the set of reaction mechanisms that utilize sugar for energy in our mitochondria. Okay? And it turns out that the equilibrium constant for this value, for this chemical reaction, happens to be 0.5 approximately. And again, that is immutable. That only depends on the temperature, but it does not depend on initial concentrations of reagents and products. So what we can do is start the reaction with, say, a concentration of glucose 6-phosphate of 0.6 molar and a concentration of fructose 6-phosphate of 0.0 molar. Then we let the reaction go, and it turns out that at equilibrium, which we're going to write as the concentration of glucose 6-phosphate after equilibrium has been reached, and fructose 6-phosphate. Okay, what happens is that this, for this particular example, where you start with 0.6 molar and 0.0 molar, the concentration of glucose 6-phosphate will be 0.4 molar, and the concentration of fructose 6-phosphate will be 0.2 molar. Okay, the reason is that for this particular reaction, the equilibrium constant has to be equal to the ratio of the concentration of products, which are fructose 6-phosphate at equilibrium, over the concentration of reagents, glucose 6-phosphate. Okay, and notice that 0.2 over 0.4, that is 0.5. That is the value of the equilibrium constant. Okay, so this is one example for how, for a particular set of initial concentrations of reagents and products, you actually end up with concentrations that give you the actual value of the equilibrium constant. Now, to demonstrate that this equilibrium constant does not depend on the initial concentrations, we could do the same experiment, but starting with 0 reagents and 0.6 molar of products. Okay, so we actually won't have this anymore. You have that you start the reaction with no reagent and all product. Well, what will happen is that initially product will turn back into reagent until an equilibrium is established. And then what happens is that after the equilibrium is established, you can measure the concentrations, and they will still be 0.4 and 0.2, such that the ratio is 0.5. And again, that's because that value of the equilibrium constant is immutable, is specific to its reaction, and it only depends on temperature. Okay, finally, we can do a final experiment in which we start with 0.3 molar of each. Okay, so equal amounts of reagents and products, and the reaction will proceed in which you're going to be turning a little bit of product into reagent, such that the final concentrations are still the same. Okay. All right. So notice that the ratio of products over reagents is still going to be 0.5, which further corroborates the idea that the value of the equilibrium constant is essentially a constant, okay, for a particular temperature. Okay, in this video we have introduced the concept of the equilibrium constant that characterizes a chemical equilibrium. In future videos we're going to see how you can write equilibrium constants for even more generic reactions than the ones that we have studied here, and we're going to pay attention to what happens when you have gases in the chemical reaction, perhaps solids, perhaps liquids, and so forth.